Hello everyone, welcome back to Math with Allison. Today we're working in our sequences and series, so we're going to be talking about the ratio test. Let's go ahead and dive into it. Naturally, we're going to start off with an infinite series here. So we have the summation k equals 1 to infinity of 1 over k factorial. The reason I introduce this first is because we often have factorials for the ratio test. So if you've never seen a factorial before, let's go ahead and go through it. So a factorial is where we take the number 3 factorial and we just multiply it by all the numbers below it until you get to 1. So 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. K factorial for a number we don't know, so k is just representing any number in that case, is going to be k times 1 smaller than k times 2 smaller than k, 3 smaller than k, all the way down until we get to 3 times 2 times 1. So we're going to go ahead and use the ratio test for this series. So what is the ratio test? We have r, which is the ratio, is the limit as k approaches infinity of the term a k plus 1 divided by the term ak. So in our case, our normal ak is going to be 1 over k factorial. And then I'm going to add 1 to k, so I get 1 over k plus 1 factorial. Let's go ahead and find r. So we're going to have r is equal to the limit as k approaches infinity. We have ak plus 1, which is 1 over k plus 1 factorial divided by 1 over k factorial. Let's go ahead and rewrite this. First, we have the numerator, which is 1 over k plus 1 factorial. And I'm going to multiply it by the reciprocal of the denominator. That's going to be k factorial over 1. Alrighty, so now let's go ahead and try to simplify this. We have the limit as k approaches infinity. K factorial is going to be k minus 1, k minus 2, all the way down to 3 times 2 times 1. Now k plus 1 factorial is going to be k plus 1 times, now we subtract 1 and we just get k, times k minus 1, k minus 2, all the way down to 3 times 2 times 1. So notice here the terms that cancel out. The k cancels, and then the k minus 1, the k minus 2, and then everything behind that is forever going to cancel. So all we're left with is that k plus 1 in the denominator. Now that we have it simplified, we can actually evaluate the limit. So naturally, as the denominator goes to infinity, this whole thing is going to approach 0. So let's go ahead and talk about the results, because what does this actually mean? When r is between 0, and it can equal 0, and 1, then the series is going to converge. So for our ratio test, since our ratio is equal to 0, that tells us that our series is going to converge. There are some other things. So if r is greater than 1, and that includes if it diverges to infinity, that means that the series is going to diverge. And then one more, when r is equal to 1, the test is inconclusive. And that's because there's some series where the ratio is equal to 1 and it converges, but there's some series when the ratio is equal to 1 and it diverges. So it could be either case. You'll just have to apply a different test. So let's look at the big idea. We know as k is really, really large, a plus 1 divided by ak is going to approach r. At some point, it's going to be approximately equal to r. So let's go ahead and multiply that ak over. So here it's like we have a little formula for ak plus 1. Now here, if we were to take the summation, so ak plus 1 plus ak plus 2, we can replace that with what it's equal to. Ak is just equal to itself. A to the k plus 1 is approximately equal to r times a to the k. Now let's go ahead and see how we found r squared a to the k. We'll go ahead and take the next one. So ak plus 2 divided by ak plus 1 is going to approach r. But we already found what ak plus 1 is equal to. So ak plus 2 divided by, that is equal to r times ak, is approximately equal to r. Now I'm going to multiply the denominator over, and we get ak plus 2 is approximately equal to r squared ak. And then you can keep doing that on and on forever, right? It'd be r cubed ak plus r to the 4th ak, so on and so forth. So what I'm going to do on that right side is I'm going to factor out an ak. And notice here what we have. We have a geometric sequence. And we know some things about geometric sequences. But first, we're going to talk about when r is equal to 0. If r is equal to 0, then at some point, we're just going to be adding on 0, right? So that's not going to make a difference to our series, which is why it's going to converge. It's like we're adding such a small number, it doesn't add very much at all. Now, for a geometric series, we know if r is between 0 and 1, then the geometric series is going to converge. which is why if our common ratio is between 0 and 1, it's going to converge. And then finally, for a geometric series, we have that when r is greater than 1, the series is going to diverge. And the same thing goes with the ratio test. If r is greater than 1, it's going to go ahead and diverge, right? It's basically saying that if the ratio is pretty large, the power of the ratio, like r cubed, r to the fourth, is just going to get bigger and bigger, and you're just adding more and more values, right? It's never going to stop adding. So let's go ahead and try some examples. We have the summation k equals 1 to infinity of 10 to the power of k divided by k factorial. Let's go ahead and find what r is equal to. We're going to take the limit as k approaches infinity. This is what I always do, is I write it as the k plus 1 term, so 10 to the k plus 1, divided by k plus 1 factorial. And remember, you're supposed to divide by a to the k. I always just multiply by the reciprocal. I just multiply by the reciprocal of the original little formula, right? So that's what I do to skip a step. You don't have to, you can write it out each time. But first, I'm going to go ahead and use that exponent rule. And remember, this is going to be k plus 1 times k minus 1, all the way down to 3 times 2 times 1, right? And I'll extend that out. And then we're going to multiply that by k factorial. That's going to be k minus 1, all the way down to 3 times 2 times 1, divided by 10 to the k. And of course, here we're going to go ahead and see what cancels out. That 10 to the k cancels, which is really nice. The k cancels, and then everything behind it also cancels. So notice here what we are left with. We have the limit as k approaches infinity. In the numerator, all we have is a 10, and then in the denominator, all we have is a k plus 1. Naturally, as k approaches infinity, this is going to go to 0. So we have, by the ratio test, this series is going to converge. Here we have another example, the summation k equals 1 to infinity of k to the power of k divided by k factorial. Let's go ahead and find what r is equal to. So the limit as k approaches infinity, that's going to be our k plus 1 term. So k plus 1 to the k plus 1, k plus 1 factorial, multiply it by the reciprocal, right? K factorial divided by k to the k. So just like last time, I'm just going to go ahead and quickly simplify those two out. All that's going to be left is that k plus 1, right? The k factorial, everything behind it cancels out. Let's go ahead and simplify, that was a weird limit, the numerator. We have k plus 1 to the k multiplied by k plus 1. That k factorial canceled out. We had a remaining k plus 1 in the denominator times k to the k. So we have something else that cancels, right? So we have that k plus 1 is going to cancel, which is super nice. So now what we're working with is a limit as k approaches infinity of k plus 1 to the k divided by k to the k. Since they are raised to the same power, we can go ahead and combine that into 1. We have that all raised to the power of k, and again, we can simplify this inside. That becomes 1 plus 1 over k. Now, this is equal to something. This is a special identity. If you know what it is, that's great. Otherwise, I'm just going to go ahead and go through and solve it. So notice here what we would have. If we plugged in infinity, we would have 1 plus 0 to the infinity, which is equal to 1 to the infinity. That is indeterminate form, but it's not in the form of a fraction, so we can't use L'Hopital's yet. So let's go ahead and set up 4 L'Hopital's. I'm going to take the natural log of both sides. And the purpose of doing that is so I can use exponent rules. So that exponent comes to the front, and I'll rewrite it to be bigger. So we have k times that whole thing. This is, again, not a fraction in indeterminate form, right? So I'm going to rewrite it as a fraction. I know that this numerator, I'm going to make it the numerator, is approaching 0, right? Natural log of 1 is going to be 0. And I'm going to rewrite that as divided by 1 over k. This simplifies to k times the natural log of 1 plus 1 over k. But notice what happens. In the numerator, natural log of 1, that's going to be approaching 0. In the denominator, 1 over k is also approaching 0. So I rewrote it so I could have a fraction of indeterminate form, and I can go ahead and use a L'Hopital's. So we have the natural log of r is equal to the limit as k approaches infinity. So here, let's take the derivative of the numerator. We put whatever's inside the natural log on the bottom, and we put its derivative on the top. And that's going to be divided by 1 over k squared. So notice what's going to happen here. We have that these values are going to cancel each other out. You can write it out nicely if you want to see how that works. But all we're left with is 1 over 1 plus 1 over k. As k approaches infinity, this is going to be 1 over 1 plus 0, which is just equal to 1. So this is not our final solution because the natural log of our common ratio is equal to 1. Now, if I have both sides, raise it to e, we have r is equal to e. And e is like 2.71 or whatever. So this is greater than 1. So by the ratio test, this is going to diverge. Okay, we have one more here. So the summation k equals 1 to infinity, e to the negative k times k squared plus 1. Now notice here there's no factorial. A factorial is really a good clue in for I want to use the ratio test, but that doesn't always have to be the case. So let's go ahead and try this one out. We have the limit as k approaches infinity, and here you can actually just write it as a fraction, right? So that's going to be e to the negative k plus 1 because I'm adding 1 to k plus 1 quantity squared plus 1, and then all of this divided by the original. So e to the negative k times k squared plus 1. Let's go ahead and do some simplification. So notice in this exponent, this is going to be e to the negative k minus 1. I can rewrite that as e to the negative k times e to the negative 1. And if you wanted to square k plus 1, you can do that. So k squared plus 2k plus 1 plus that additional 1 on the outside, and all of this divided by e to the negative k times k squared plus 1. So again, we're going to notice what cancels out. First, we have that e to the negative k cancels, and so far that's the only thing that cancels. So we have the limit as k approaches infinity. We have a scalar e to the negative 1, which you can write as 1 over e, or leave it as e to the negative 1, doesn't matter. And notice here that we're working with a limit at infinity. That means we can take the highest power of the numerator and the highest power of the denominator. And if they have any scalars, they have to stay. So 1 over e has to stay. And we get multiplied by k squared over k squared. So here we can simplify this, right? Those divide out, and all we're left with is 1 over e. And the limit of a constant is just equal to that constant. So here our ratio is equal to 1 over e. That is going to be smaller than 1, which tells us that the series will converge. And there we have our solution. So that's all I have for us today. If you enjoyed this video, I have many more like it, so make sure to check out my playlist. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.